Inverse trigonometric functions. For every function, there is an inverse function, including trig functions. A real simplistic way of thinking of what an inverse function is to describe it as being a function that undoes everything that another function had done. Okay, so let's consider how we've been using trig and start thinking about how we can use it backwards. The sine of 30 is equal to 1/2. The cosine of 60 is also equal to 1/2. The tangent of 45 is equal to 1. Okay, so what do all these functions do? These functions take angle measurements, whether they be in degrees or radians. They take angle measurements and they figure out a ratio that goes with it. By definition, the ratio that we get from the sine is going to be the comparison of the y value to the radius when drawn in the unit circle. The cosine is going to give you the x value compared to the radius in the unit circle, and the tangent is going to give you a comparison of the y value and the x value from that unit circle. They take all these angles and they give you back a ratio. So the inverse function needs to work backwards. It needs to do everything completely opposite. It needs to be able to take that ratio and give you back an angle. Okay, the inverse trig functions use ratios to find angles. That's what they do here. If the original functions take angles and they give you back ratios, the inverse trig functions are going to need to do this backwards. They're going to need to take your ratios and give you back angles. Let's take a look at the first one here. The sine of 30 is equal to 1/2. Okay, if we're thinking backwards, that means that we don't know what the angle measurement is, but we have the ratio. We would have some problem that would maybe say the sine of theta is equal to 1/2. And we're trying to figure out what that theta is. So we have to use an inverse function to undo the sine. And that inverse function is going to be called the arc sine, or you can even just call it the inverse sine. I'm going to refer to it as the arc sine. We're going to take the arc sine of both sides of the equation, and that will actually solve for theta. And here's what it would look like. I'm going to need to just write it to the side here. The arc sine is going to look like this. It's going to be sine with a -1 as an exponent, and that indicates that you have an inverse. Okay, so we're going to use that and place the sine of theta inside of it. Likewise, on the right, we're going to use the arc sine and go ahead and place the 1/2 in there. So we've taken both parts of the equation and then plugged them into the arc sine or inverse sine. On this side here, if you take the sine of theta, then the arc sine or inverse sine is going to undo that part, and we get the theta by itself. So in summary, the way that we can look at this is to do the problem backwards, you can actually just take the arc sine of your ratio. And if you take the arc sine of the ratio, you get your angle measurement. Okay, so for the next one here, cosine 60 equals 1/2. If we were looking to solve for that angle 60, but we knew the ratio is 1/2, you could evaluate the arc cosine of 1/2, and that will tell you 60 degrees. You can do the same thing for tangent. You can do the arc tangent of 1, and that will give you your angle measurement back. Okay, so let's take a look at that in the calculator, just so that we can see that it does work. First, the sine of 30 degrees is 0.5, 1/2. All right, now the claim here is that if I take the arc sine of 1/2, I'll get back 30 degrees. All right, now to type that in this calculator, I have to press second. Most calculators, what you'll do is you'll have to do a shift. When you do that, it will allow you to type in the inverse sine or arc sine. So I can type that, but you definitely want to see that -1 for this part. I'm going to type the ratio in, and that's going to come back as 30 degrees. Now we had there. Now I'll do the same thing for cosine. So arc cosine of 1/2, that's going to come back as 60 degrees. Works out. And we're going to do the arc tangent of 1, and that's going to give us back 45. So here's the tricky part about inverse functions and trig. For a function to have an inverse, it must be 1-to-1. That means that no two inputs have the same output. The periodic nature of a trig function fails to be 1-to-1. However, if the domain of the trig function is cleverly limited, it is 1-to-1. So we're going to be doing that. We're going to limit the domain so that we can make all of this stuff work and resolve the issue. 1-to-1. No two inputs have the same output. Remember that with an inverse function, you would be taking an output from an original function and backtracking to get the inputs here. Okay, we don't want to have multiple inputs have the same output. We want to be able to start with an output, put that into our inverse function, and know what we're going to get as a response. But if you have a lot of inputs that go to that output, you're going to get too many answers. You're going to get too many answers from that inverse, which means that it fails to be a function. Okay, let's take a look at it in the tangent function here. You've got this periodic function that keeps waving over and over again, right? And actually goes on forever. There's an infinite number of these little waves in there. All right, let's just consider the output of 1, which is up here. Let's consider that output. At that output of a 1, you have an infinite number of inputs that give you 1. Here's 45 degrees. We just looked at it above. We saw that the tangent of 45 gives you 1. Okay, we saw that. But there's other places over here that do the same thing. There's a spot right here that does the same thing. So there's all these different angle measurements that are going to be giving you outputs at 1. Okay, so if you do an inverse function and you said, all right, tell me what angle measurement has a ratio of a 1, well, there's an infinite number of choices to it. Of course, the calculator, when we typed this in and we did the inverse of 1 for tangent, we actually got back 45 degrees as the answer, and that was the only answer it told us. Okay, so what we end up doing to make all of this work out right is we limit the domain to only one piece where we're not going to get repetitive answers. In this case, the chosen portion that we're going to limit it to will be that middle wave, the one that goes through the origin. Okay, we're going to let that be the only part that we consider when we do an inverse tangent. That's what the second picture shows here. It drops out all the repetitive waves that are around it and then just keeps that one. So that if we were now to do an inverse tangent of 1, we could go look at 1 and notice that there's only one output. So that's going to match up to that value, which would be 45 degrees and 90. Now recall that when we talk about the graphs of functions and their inverses, they're actually reflections over the diagonal line y equals x. So if I took this graph here, which is the limited domain of tangent, and let's see if I can do this right here, and drew the line y equals x through it, and then reflected over it, it actually becomes this image here. And when you look at that reflected, that is actually the picture of arctangent. That is a picture of arctangent. All right, one more thing here. Remember that previously I had typed into the calculator the arctangent of 1. Let me go ahead and show you that again. I type in the arctangent of 1, and the calculator gives me back the answer 45. Okay, it told me that it was 45 degrees, and it didn't give me back any of the other answers that would have corresponded to having a ratio of 1. So the calculator is well aware of the domain that we have restricted the tangent function to. In fact, we have restricted it to just a couple of quadrants here. Right here, from the origin over to pi over 2, that's 0 to 90 degrees. That's actually quadrant 1. Okay, so we're going to be using quadrant 1. If you go back the opposite direction, that is actually quadrant 4. So we're thinking that we're rotating backwards 90 degrees, so 0 to 90. Okay, so when you do an arctangent, whenever you do an arctangent, you will never get answers back that are here, at least as we do it in the calculator. Now, if there's relevance of answers in these areas, for whatever we're working on, it becomes your responsibility to use reference angles and figure out what those angles might be. But the calculator by default is only going to give us answers that would correspond to quadrants 1 and 2. And if it is a positive ratio, if you start with a positive ratio that you're using, it's going to give you back an answer that's in quadrant 1. If it is a negative ratio, it's going to give you back an answer that would be in quadrant 4. Okay, tangent is positive in quadrant 1 and negative in quadrant 4. Like tangent, sine and cosine are also periodic functions. So if you're looking for an angle measurement that corresponds to a certain ratio, you're going to get an infinite number of answers to go along with that. Okay, so like in tangent, we're going to limit the domain. We're going to crop it off so that we're not running into that problem. Okay, these are the places that we're going to limit them. Okay, for the sine curve, we're going to do the exact same section that we used from tangent. We're going to go from negative 90 degrees to positive 90 degrees. That means that we're going to be using quadrant 1 and also quadrant 4 for sine. Okay, if we take just that piece of the graph and we reflect it over the diagonal line, y equals x, it gives you this picture. So this would be the picture of the arc sine. That would be the picture there. All right, and again, we are only going to be using quadrants 1 and quadrant 4. So quadrant 2 and 3 are out. And again, if you do have an answer that could exist in that spot, like there's a relevant answer to that area, you would need to use reference angles just to figure out what that answer could be. But the calculator is only going to give you answers back that would correspond to the first and the fourth quadrant. If it is a positive ratio that you're using, you're going to get back an angle that would be in quadrant 1. If you're using a negative ratio, you're going to get back an angle that would be in quadrant 4. So that is identical to what you see for the tangent. For cosine, we're going to have to use different quadrants here. Okay, if you just went with quadrant 4 and you use quadrant 4 and quadrant 1, well, you draw a horizontal line through that and you're going to see it's crossing at 2 places. So that wouldn't be the best place to choose for your inverse cosine. Okay, what we'll actually be using is from 0 to pi. That piece right there doesn't have any issues with multiple inputs corresponding to the same output. So we're going to choose this part here, which is going to be quadrant 1 and quadrant 2. All right, so we're using 1 and 2. That means we're not using 3 and 4, at least when you evaluate in the calculator. And once again, if you do have answers that could exist in those quadrants, it just becomes your responsibility to use reference angles and find them. Okay, but the calculator is going to give you back answers with quadrants 1 and 2. If it is a positive ratio, it's going to give you an angle measurement that would be in quadrant 1. If it is a negative ratio, it will give you an angle measurement that would be in quadrant 2. Okay, so that one's different than the others. The sine and tangent both give you answers in these quadrants, but the cosine, you're going to get answers that would be here. All right, example number 1. This is going to get about as straightforward as you can with the problem. All we're going to do is use a calculator to evaluate the arctangent of 2 and the arcsine of square root 3 over 2. A couple things before I do it though. You're going to notice that these have capital letters on them. This is capital T and that is also capital S. When you do see that printed, it is indicating that your answers are going to be coming from that restricted domain. Okay, that means, remember, tangent, sine, both of those are only going to be giving you answers that would have referred to quadrant 1 and 4. Okay, so when you see the capital letter, that actually implies that we have that restricted domain. All right, so let's go ahead and type these in here. Now, trying to find a spot to put that. All right, now when I take the arctangent of 2, it is not going to pop up with a capital letter, but whatever answer I get is the one that I accept, and I don't worry about answers from other quadrants. All right, so I have my calculator set for degrees right now, which means that the arctangent of 2 is going to be equal to 63, let's say 63.4 degrees. Now, you can switch your mode because we are going to be going back and forth between degrees and radians, so let's go ahead and practice that. We can switch this over to radians, do the same problem, and you get that answer. All right, so that would be in degrees. It is also equal to 1.107 radians. Okay, both of those answers are just different types of units that we have for angles. All right, the arcsine of square root 3 over 2, that is referring to one of our special angles. I hope that you remember which one that is, but if you don't, well, it's going to tell us as soon as we type it in. Actually, let me get this in degrees, because we're going to recognize that answer better than we will the radians. All right, the The arc sine of square root 3 over 2 is going to give you back 60 degrees. All right, so the arc sine of square root 3 over 2 is equal to 60 degrees. In terms of radians, that would also be pi over 3 radians. Okay, now I'll verify that one here. Go ahead and switch the mode over to radians. Type it back in. Now when I press enter, I'm not going to get this answer. I'm going to get a decimal form of that answer. However, pi divided by 3 is that number. Examples 2 and 3 are actually the same problem. They're the same problem that we have here, except that in example number 3, we're going to talk about how we can do this problem without a calculator. All right, so example number 2 is very straightforward. You can literally type the entire thing into the calculator right now. Okay, and that's all the work there really is to. So I'm going to type in cosine. It's going to open up the parentheses. Type in the arctangent. We got the parentheses open up. We're going to be using -2 over 3. So I'll type that in, make sure I close twice, press enter, and that's it. That's the whole answer. Really what's happened here, and the calculator did all the work for us, it took a ratio and it found the angle measurement that would have correspond using the arctangent, okay? Once it had that angle measurement, so you can think of all of this as an angle measurement, that angle measurement went into the cosine and we got back that answer. So this would represent a ratio. It is in a decimal form, but it would represent a ratio. Okay, so this part found an angle. That angle then went into cosine and we got a ratio back. Okay, so this is equal to 0.832, we'll just go to 3 decimals. Example 3 is going to have us do the same problem, but without the use of the calculator. However, we are going to compare our answer when we're done to the answer that we got from the calculator, just to see that this all works here. All right, working from the inside out, we have a ratio and we want to figure out the arctangent of that ratio. Really what that means is you're finding an angle that would correspond to this ratio. Okay, so I'm going to draw a picture, that same picture we've seen a lot of times, okay, which is going to be the axes with a circle around it. Okay, so this part right here where it says with a capital T, the arctangent, when it says that, we're going to be designated certain quadrants to look at. Okay, so for an arctangent, you're either going to be using quadrant 1 or quadrant 4. Okay, so these are out. When we typed into the calculator, it also knew, don't look over here. The angle is not going to exist in that spot. Okay, now if your ratio is a positive number, you'd be in the top quadrant. If you're a negative, then you're going to be in the bottom quadrant. Our ratio is a -2/3. That means that our angle measurement is here. It's in quadrant 4. All right, so let's think about the definition of tangent. Okay, the tangent of theta is equal to the y value divided by the x. So the y value is going to be a 2. The x is going to be a 3. Okay, so we're going to move out a little bit more than we would down. Okay, so I'm going to go ahead and put a point here. I didn't measure everything exact, but 3 is bigger than 2, so I want to make sure that I can at least see that in the picture. In addition, we have a negative, right? We have a negative. Well, to the right is positive, but down is negative. So that's, I'm going to try and squeeze it in there. That's where the negative goes. It's a -2 that's here. All right, and I'm going to go ahead and just draw this line because we're eventually going to need it. Okay. All right, so the arctangent of -2/3 is going to find an angle measurement. It's actually going to find this angle measurement here. It's going to solve for that angle right there. All right, and we don't actually need to do this, which is really cool here. We don't actually have to do the arctangent part and figure out what this angle is, because there's another part to the problem, which says that we're going to take that angle and we're going to put it inside of the cosine. We're going to take whatever this angle is and we're going to put it inside the cosine. Okay, so if I just evaluate this now as the cosine of that angle, I can go back to the definitions of cosine. The cosine is x divided by r. X divided by r. So I don't need to know the angle. I just need to know in this picture what is x and what is r. Okay, so our x is the 3. We got that much. We don't know the r value, but with a little bit of Pythagorean theorem, 3 squared plus 2 squared, we get 9 plus 4, which is 13. So our radius is equal to the square root of 13. All right, and now before I clean that up, let's just go ahead and check and see that this is really the right answer. My claim is that this is it. This is the whole answer here, the whole answer to that. All right, now, recall the calculator gave us 0.832. Okay, so let's type in 3 divided by the square root of 13 and see that we get the exact same answer. All right, now we don't like that answer because there's a radical in the bottom, so we're gonna fix it up. We're gonna multiply the top and bottom by square root 13, which means we got 3 square root 13 over 13. That would be the cleaned up answer, which I'll go ahead and just type in so you can see that as well. 3 square root 13 divided by 13 is the same answer.
Wait, what?